So the next session will be by Mr. Binayak Lohani, and on the topic will be scalar transport foam. But he is there, but we will be playing a video that he has recorded because he was not sure about his presence during this time of the workshop. So Abhushan, could you please play it? And I hope Binayak is there. So if you have any questions, he can answer.
Yes, ma'am.
Hello everyone. First of all, I'd like to thank the FOSSI team for organizing this workshop on OpenFOAM and inviting me to conduct this session on scalar transport form. I'm Binayak Lohani. I'm currently pursuing aerospace engineering at Pulso campus in Nepal. I'm also a technical contributor at FOSSI. Talking about my past experience with FOSSI, it's been really wonderful. I did my previous internship at FOSSI where I used OpenFOAM to conduct CFD analysis. So my work also got accepted, and I presented my work at Fluid Mechanics and Fluid Power Conference. So I'm very grateful to the FOSSI team. Since then, I have been using OpenFOAM to conduct several CFD analysis, and two of my case studies have been published in the CFD FOSSI website as well. So you can check out my work there too. So let's quickly move towards today's session on scalar transport form. So this is the outline of today's talk. First of all, we'll see how a scalar transport form transport equation looks like. Then we'll see a scalar transport form solver in OpenFOAM. Then we'll talk about the limitations of this solver and see how we can modify this solver to incorporate the limitations that we have here, and also see one example for this. So this is the scalar transport equation. It's also known as the convective diffusive equation. Here key is the scalar term. The first term is the unsteady term. The second term is the convective term. Here ui is the velocity field. The third term is the diffusive term, where df is the diffusivity constant. So the diffusivity constant d is the molecular diffusivity, and nu t and the ratio of nu t and sct is the turbulent diffusivity. Okay, so nu t is the turbulent viscosity and sct is the Schmidt number. So Schmidt number is a constant. We have to pick a particular value to get to solve for this case. The last term is the source term, and combining all these four terms gives the scalar transport equation. So the scalar transport form, it's a basic solver that resolves the convection diffusion scalar transport equation using a user specified stationary velocity field. So user specified stationary velocity field is needed because in the previous equation we saw the velocity field. We do not solve for the velocity field here, but it needs to be specified, and it's stationary throughout the simulation. Okay, we'll further talk about this point later also. So remember this point. The second point is it's transient and incompressible solver. The scalar term is passive. So the passive scalar means that it does not influence the fluid properties, for example, the viscosity or the density of the fluid. Next, we'll see how the scalar transport form code is coded in the OpenFOAM. This is a simple C++ syntax. So below one is the actual equation, and it's coded in this fashion. So the unsteady term is ddk, and the convective term is the divergence of phi k, where phi is the flux. So the third term is the Laplacian dtk. So this negative sign is because this term comes to the left hand side. Mm, and the last term is the fp modulus dot source k. This is the source term. So we'll see how the case is set up in OpenFOAM for this solver. We only have one case, speech daily case, in the tutorials, and the folder is present in this directory inside form tutorials basic scalar transport form speech daily. Okay, so as we have already known that OpenFOAM folder contains three subfolders: zero, constant, and system. Inside the zero folder, we have to define the initial and boundary conditions. So here in this case we have t and u. Here t is used instead of k. In the previous equation we have seen k as a scalar, but here t is used as a scalar. It's just an indication. Particularly here t is the temperature. So temperature is also a passive scalar term. And u is the velocity field. So we define the initial and boundary conditions in this case. Inside the constant folder, we have the transport properties file. So in the transport properties file, we have to define mm, the constant parameters. So in this case, the only constant parameter is the diffusivity constant. Okay. So since temperature is used here, the diffusivity constant is can be referred to as the thermal diffusivity term. So we define that here. And inside the system folder we have three files: control dict, fb schemes, and fb solution. So all these files are used to define the time control and the discretization schemes, the algorithms that are used to solve for the scalar transport equations are defined in these files. Okay, we'll see this one by one later. So this is how the case looks like. It's a 2D case, and this sort of geometry is also known as the backward facing step. So this is the inlet, this part only, and this is the step. Okay, these all are the walls. The rest are the walls, and this is the outlet. So what happens is the flow from the inlet will recirculate in this behind this step and flow towards the outlet. So that's why it's called the backward facing step also. It's a 2D case. So we have to predefine the velocity field here. It remains constant throughout the simulation. It does not change. The only thing that changes is the scalar term t, that is evolved from inlet to outlet, but velocity field remains constant. It's already defined in the zero folder. Okay, we'll see this. Next, the passive scalar t field in the initial time step at 0 second t, it's defined as 1 at the inlet only. Okay, this is initial condition. So it's 1 in the inlet only, and at all other places it's 0. Okay, you can see here from the color bar also. And this is the last time step. The right hand side is the last time step. So we can see here at last time step how the scalar term t evolves or gets transported towards the outlet. Okay, in this fashion it's transported. Later on we'll see the animation. Now we will do one hands-on session to run these cases. It's a simple case now. So I'll request all of you to please open your terminal. It can be you might be using Ubuntu or WSL. It doesn't matter. For now, I'm using WSL. Okay. So we have to copy the folders. This folder, as I have already shown where the folder is present. So we have to copy this folder in the present directory. To do this, please follow my command. It's pretty simple case. So please type cp -r after then please type this. The code is case sensitive, so please take care of the upper and lower case alphabets. So foam tutorials slash basic, then after that scalar transport T capital, transport, and foam F capital, then it's tally. So after writing this command, then we have press space, then press full stop. So full stop meaning that we have copied the folder from this location to the present location. Present location is indicated by this dot. Okay, so after typing this command, please type this command, all of you, and then we can type enter. So after this we can list the present directory, and we can see tally is present here. Okay, so all of you please write this command and press enter. So now we can move into the tally case. its daily case. So now if we list it, we can see the zero, constant, and system folder present here. The all run file is used when we have to run all the commands all at once. So we'll see this later. First of all, let's see the zero folder. So inside the zero folder, we see the T and U files. So one by one, let's see how the boundary conditions are defined here. So I use Notepad as a text editor. You might use any text editor of your choice. To use the Notepad, you please type notepad.exe, then type T to see the files of T. So the boundary conditions for the scalar term T is given here in the boundary field, as I already showed you that uh, in the T is defined as 1 at the inlet, and at all other places, outlet, upper wall and lower wall, is 0 gradient. So if considering T as temperature, the 0 gradient means that it's the adiabatic condition. Okay, and for the front and back, it's empty because it's a 2D case. So now let's see the velocity field. Okay, now velocity field. As I already told you that velocity, we don't solve for velocity, but we have to predefine the initial conditions for all the cells in the domain. Okay, so this internal field are all the internal cells. Uh, so we have to define it as a vector in x, y, and z direction, since velocity is a vector. And we have a long list here for individual cells of the pitch daily case. Okay, and at last we have the boundary conditions as well. So at the boundary conditions, inlet is 10 meters per second in the x direction, outlet is 0 gradient, and at wall it is no slip condition. Okay, so here we have to define at in boundaries also, and also at the internal cells. Okay, so after this, let's move on to the constant folder. So to move backwards of this case, since we are in the um, zero folder now, we have to move one step backwards. So we have to click cd double dot, press enter, then we'll move backwards. Then list let's move into the constant folder, cd constant. So inside the constant folder, we list it as transport properties is only present here. To see the transport properties file, we'll use notepad. So notepad.exe, then transport properties. So if we see the contents here, we only have dt. This is the diffusivity term. So since T is the temperature here, it's thermal diffusivity, and the value is 0.01. Okay, so this square, in the square bracket we have the dimensions. And this is the thermal diffusivity value. So after this, let's see the system folder. We can see, type this command, then we move to the system folder directory. Now we can see that control dict, fp schemes, and fp solution. Inside the control dict file, let's move to the control dict. Now we can see the time control is present here. In the application, we have the name of the solver we are using, that is ScalarTransportFoam, and rest are the time control. For example, the start time is 0 second, and stop time, this end time is 0.1 second. So this is the end time, and delta t is this. So rest are the functions. For example, write format, we can write it as ASCII or binary, and rest are the functions that are required to run the case. Okay, after this, let's see fp schemes file. So inside the fp schemes, we have defined the discretization schemes for various terms. For example, the unsteady term, for the unsteady term, ddt schemes is used as Euler. So as we know, Euler is a first order accurate term. So we can increase the order of accuracy to maybe second one, maybe backward or Crank-Nicolson. So we can use that also. So we have to take care of the stability also if we want to increase the order of accuracy. So and gradient schemes is Gauss linear, divergence schemes is for phi t is Gauss linear of point grad t. So we can change this input also, but we have to take this value carefully. Okay, it also depends on case by case basis. Now next we'll see the FP solution file. Inside the FP solution file, we have to define the solvers that I used to iteratively solve the T or the passive scalar term. So the solver name is PBIC is step, preconditioner is used, and the tolerance is given, and the relative tolerance is also 0. So these are the input that are necessary to run the cases, and simple algorithm is used to solve the transport equation. Okay. So these are all the files present here. In the system folder, we should have extra file also to run the mesh. So we don't have it here, but if we look at the all run file, all run. Sorry. If we look at the all run file, you can see here. These are the commands that will be run if we run directly with the all run file. We need to find the blockmesh file also. The blockmesh strict file is present in some other directory, form tutorials, resources, blockmesh page daily. So in this case, we can run this whole command all at once, so that the blockmesh strict file will be copied, will be run in this current directory. Okay. So if I run this file, run this command, then blockmesh dict file will be run. Since it's present in some other location, okay, it's not present here. It doesn't matter much. We can copy here also. So if we press now enter, we'll run the blockmesh file. Okay, now mesh is already generated for here. Now next command, we only have two commands. The next command is the name of the solver. So the name of the solver is ScalarTransportFoam. So if we hit this, press enter, we will run this case. So here we can see we are only solving for T. We are not solving for U. We are not solving for P, velocity or pressure. So we are only solving for T. Velocity remains constant. So the end time step is 0.1 second. So it's completed now. So end time, we are only solving for T. To see the results, as we have already seen some of the results in the slides also, we can see the results in ParaFoam. I'll show you the animation. How it's done. Okay, in the ParaFoam, I think you don't need to run this. I will just show you quickly. So this is the pitch daily case, and if you want to see the first of all the velocity u field, so it okay, velocity u field, it remains constant throughout. This is time 0 second, but if I run this animate button, it doesn't change. Okay, it remains constant throughout, as we are not solving for velocity. I already told you that. But if let's move to the 0 second also now if you see for this t file, it's 1 at the inlet and 0 at all the places in 0 time. Okay, 0 second. Now if I click on play, you can see the animation. Okay, how it is transported. So you can see how this t is transported in the domain. So it's reduced now, but we need to scale it to see completely. If we scale it, this is the final time step at 0.1 second. Now we can see at how this scalar field is transported in time in this domain. So this is a simple example. You can run this on your own and see how the result changes. Now we'll see the limitations of this solver in the slides.
So,
To see talk about the limitations. An option to solve for the flow coupled with the scalar transport is not available. So we cannot solve for the flow, that is the velocity and pressure. we only solve for the scalar transport, that is T in the previous example. Okay, so that's one limitation. Now, the diffusion coefficient is assumed to be a constant scalar, so it's a constant scalar. Here we cannot change this. So there are two limitations. The first one is Navier-Stokes equations cannot be solved along with scalar transport equation, and second is diffusion coefficient is constant. So to overcome the limitations of scalar transport form, the transport equation can be coded inside solvers, inside other solvers like simple form that is steady state, and ICO or PISO or pimple form that is transient solutions. Okay, so we can code the scalar transport equation into some other solvers. So why do you need to do this? Because we might need to simultaneously solve for pressure and velocity using Navier-Stokes equation, and also want to solve for the scalar transport equation also. So for example, in the pollutant dispersion flow in an urban flow setup, we can consider concentration of pollutants. Okay, concentration of pollutants as a passive scalar quantity, and simultaneously we want to solve for pressure and velocity field also. So in such cases, we might need scalar transport form combined with other solvers like simple form, pimple form, piso form, etc. Okay. We'll see, this is a basic introduction to such cases. We'll see examples of this in the later session, where uh, Mr. Krishnakant sir will help with the icoform solver coded with scalar transport form. Okay, and the next session. Okay, so this is how the code looks like for a scalar transport equation merged with a simple form. So while the simple form solver is running, we incorporate this scalar transport equation in this fashion. So it's a simple way to illustrate such cases, and we define this we define this diffusivity constant in this way. A decay is the molecular diffusivity plus nu t and Schmidt number. Okay, this is the ratio. We can use this code. So talking about the example, this is a street canyon setup. So for context, a street canyon setup is a place where there is a narrow road on either side of tall buildings. So on either side there are tall buildings, and there is a narrow road between it. So in this case, what happens is when the mean wind direction is perpendicular to the street or road. So this is the 2D view or cross section of this case. So when mean wind is perpendicular, then what happens is recirculation region will be happening here, forming the primary vortex. So when the pollutants from the vehicles escape from these vehicles, and it gets trapped inside this region only. Okay, it revolves around this region only from in the primary vortex region, but cannot escape outside of this region. So this creates a problem of pollution. Pollution will be increased so much that it's one of the major problem of the urban city. So for such cases, we can optimize the shape of the buildings, do that sort of analysis using CFT, using such solvers. Okay, using merged solvers of simple form and scalar transport equation, and the pollutants can be considered as the passive scalar term. So with a similar intention, this is one example where scalar transport equation is used in simple form. So this is the domain where pink blocks are the buildings, okay, are the buildings, and this between these buildings is the pollutant line sources. So we consider these line sources as the passive scalar term. Then we also need to see the pressure and velocity equation and solve for it. The velocity will be from x along the x direction, so that it is perpendicular to the street. So here is the result. Okay, this is the cross-sectional view. This first one is the velocity contour plot. You can see the velocity along the x direction. It looks like this. And the next one is interesting one. This C is the pollutant concentration. Okay, So this from the line sources we can see how this passive scalar term pollutant concentration evolves, and we can see that it is unable to escape out of this urban canyon setup. So we can optimize the shape of the buildings or roof so that these pollutants can escape out and does not have the problem of pollution. So that's the one main objective for this case. So for the codes and the similar case study that is used here, you can go on to this link below where we have the codes that most solver, but the case study is different. Here the case study is that we have a isolated building where the pollutant sources are these red four blocks. So when the flow is along the x direction here, along with the flow, this pollutant sources also disperses. Okay, to see how is it is dispersed along with the flow, we are using this setup. So this is the setup from ZVAL A15 building, Longo et al. 2019 from the wind tunnel experiment. So you can go on this link. The name of the case study is pollutant dispersion modeling using CFD, a walkthrough of solver development in OpenFOAM. So this is developed by me. You can go through this, and if you have any doubts, any questions, you can contact me on this email, contact cfd@fossey.in, indicating my name. So I'll be happy to help if you have any doubts about it. So that's it for today's session for me. Thank you for being wonderful audience. Thank you.
Thank you, all of you. I would like to know if you have any questions about this session. I think most of you are wondering how the velocity field will come out of. So how we'll get the velocity data to run the scalar transport form solver. So for that, first of all, you will need to solve using another solver. For example, simple foam or potential foam, without any scalar term in it. Okay, it's a simple steady state case. First, you run that with the same geometry, then extract the data from your last time steps and put that in your initial conditions uh, in the next simulation that you want to run. So that's how you will get that. Okay, and for the next case that we discussed now, for the merge solver, you don't need to do that. We'll simultaneously run both the equations. So that's one advantage of the later version of merged code that we used. So any other questions you can ask now, or you can also contact by email.
So Aveen here was asking why internal field for T is 0. So in the previous session, I had told that internal field must for temperature must be greater than 0. In that case, like in previous case, we were actually solving the energy equation that involved temperature. But here we are not solving energy equation. Temperature is just a scalar properties or a scalar parameter that is being transported with the velocity. So in this case, we need not need to be worried about that.
Rajnesh was asking, what if we have analytical solutions for velocity? So in that case, I think you might have analytical solutions at the inlet. So you need to use the coded boundary condition for that and use merged solver to solve this problem. Okay.
Another question from Chintak Bina in the chat box.
So if there are more than one scalar transport, yeah, you can use you can solve using scalar transport form or the merge solver if you have more than one. So you need to define more than one separate. You need to define the passive scalar separately with separate name for that case.
Okay, one more question in the chat box.
So okay, how does viscosity property is included in momentum? Okay, for the merge solver, we can use viscosity also in the transport properties file. So in that case, we can incorporate the viscosity property also while we are solving the flow. It's not only for diffusion, there is convection also in the flow in that case, convection or advection. Inside constant folder in transport properties. So first case was only for scalar transport form, so there was no viscosity included, as we are not solving for Navier-Stokes equation or momentum equation. But in the next case, we are solving for velocity, pressure, and transport equation all at once. So we need to define viscosity inside that folder. Okay, constant transport properties. Any other questions? Or I think we can move.
I don't think they have any more questions. So we will take a break for lunch now.